Hello everyone. Our team will present our project proposal, which is about black box adversarial attack. This is the outline of our presentation. We're first going to motivate the problem, then talk about the baseline methodology, followed by solution and evaluation parts. If we formulate our problem just in one sentence, it is devising a black box adversarial attack that is simple but effective across multiple domains. So here we need to elaborate on the terminology we are using. The first one is adversarial attack, which is basically a machine learning technique attempting to fool models by supplying corrupted input, as you can see from the example below. When a small noise is inserted to the original input, it can be undetectable to humans, but at the same time, it may produce a completely different output by the network. So this image is originally classified as peak, but with small noise inserted, it gets classified as airliner. Another term which needs explanation is black box. It's attack done without knowing the internal structure of the model, as opposed to the white box, where we are aware of this structure. So in black box, we can only utilize the output as feedback. If we go back to the problem statement, it was devising simple and effective adversarial attack, but what do we mean by simple and effective? Basically, by simple, we mean search-based, while by effective, we mean high attack success rate, small number of queries, small distortion from the original input, and simultaneously fuzzing. Next, we need to also mention the domains that we want to consider. Since adversarial attacks are more explored in image domains, we want to go beyond that and explore non-image domains such as audio and NLP, as given in these examples. And finally, we want to clarify why adversarial attacks are important. Basically, adversarial inputs may pose serious security risks to AI software. For instance, as you can see from this animation, autonomous cars may be seriously corrupted by adversarial inputs. And also, we want to know that black box attacks are the realistic setting in software engineering, since softwares usually don't disclose the internal network structure, but only release the API. And now we will talk about the baseline methodology.
So now we know what adversarial attack is and what black box is. There is a black box classifier, and we want to make an input that will fool the classifier. In order to achieve this, the related paper suggests an algorithm they call the DeepSearch. And it is important that you understand how it works before going into our proposal. So what we have are the original image and the access to the classifier. The only information to make searching decision is the probability output of the classifier. And as the name implies, we'll be using a searching method assisted with core reduction and difference reduction. And you might be wondering what is core reduction and distance reduction. To simply put it, the goal is to find an input that will get us a wrong output, but we don't want to ask the black box too many times, and we want our adversarial input as similar as possible to the original one. So how does it work? So this is how the search is done. In an image, every pixel has a value. So a pixel represents a line of numbers, and the domain we will be searching will use every pixel as an axis of the search space. So if the image is 100 pixels by 50 pixels, we have 5,000 dimensional search space. On the right is an example of a search space with 2 pixels. That's 2 axes for each pixel, so the search space is 2D plane. The 2 pixel image that we have now is represented as x0. The lines are the boundaries of the classifiers. If the image x crosses the boundary, it is classified as a different class. And when we evaluate the image with a black box, we get the probability output from the classifier. And the fitness we'll be using is how much probable it scores in other categories. So from the last black box illustration, we favor if dog probability rises or any of the others probability rise. So for example, moving from x0 to x1 raises probability of class 1 and decreases probability of class 2 because it gets closer to the boundary. To make the matter simple, DeepSearch uses fixed size of step. So every step of any pixel will add or subtract the exactly same amount to the pixel. So with a more clear view in mind, what the algorithm actually does is it looks for direction that will get us closer or over the boundary and simply add or subtract depending on the direction. So we take an exploratory step on an axis. If the probability of others rise, we stay there, and if not, we go to the opposite direction. This process is repeated until we get adversarial result. And in order to make the image look more similar to the original one, after finding the adversarial input, DeepSearch performs iterative refinement, which is basically narrowing down the step size as long as the output stays misclassified. On the illustration here, the step size is reduced as long as it is misclassified. But you might be wondering, if the image is 5,000 pixels, doesn't that take a lot of queries? So to deal with the problem, DeepSearch modifies a block of pixels at the same time. So for instance, in a 5,000 pixel image, we can chunk 25 pixels as 5 by 5 block and reduce the search space to 4% its original size.
Here is our solution, also the goal we want to achieve in this project. We want to replicate the paper, improve the baseline methods, and expand to different domains. For replication, first we need to migrate the neural classification network, which will be our black box model. Then we'll write the code for adversarial attack with query reduction and then the refinement process. We would like to attempt the attack in a more difficult setting to improve the algorithm. The first setting is the targeted attack. The current attack only needs to output an incorrect class, while targeted attack needs to output a specified class. This is more challenging but more dangerous. Imagine a hacker is trying to use adversarial input to attack the cache recognition of an ATM machine. He makes multiple fake inputs, all results in the prediction of some very big amount of money. It's hard to make such an attack, hence it's also hard to defend. We would like to test our algorithm in this setting. The second setting is categorical feedback, which is true for several real-life softwares. In this setting, we only have the predicted label, not the probability, but we still need to have some way to estimate this probability. And our proposed method is the Monte Carlo approximation, where we run the model multiple times with some additional Gaussian perturbation and use the frequency as the probability. To move this algorithm to another domain, we need to do some adaptation. For now, the paper only studied about image domains. We would like to expand, starting with a more straightforward domain, audio, and then advancing to a more complicated one, NLP. Note that for the algorithm to work, the input that we're trying to make adversarial attack must be in the vector or matrix form in order to perform the search-based algorithm. For image, the data is inherently a matrix, but for like audio and NLP, it's not that straightforward. For audio, we might use raw data, which is in time domain, but also very popular is the use of frequency domain. An audio wave is essentially a composition of multiple frequencies whose intensity is shown in the spectrogram. This spectrogram is kind of a footage or the pictures of the sound, and we can use this spectrogram in a very similar way with an image. And for NLP, we also need to make the vector representation for the text. Some well-known word embedding that can be used include word-to-vec or glove.
We identified several datasets and models to use during our project. For audio, we are using the following datasets. And our model is music genre classification models that they are based on ANN, RNN, and CNN. For the text, we're using the following datasets, and our model that we're using is text sentiment analysis model. It's based on BiLSTM. And the novelty of our project lies in the fact that most of the studies done before are mostly focused on making attacks to image classification networks. And the aim of our project is to expand the study to non-image domains, which are much less studied compared to computer vision. And the evaluation method that we're using for our project has 3 factors. They are success rate, percentage of inputs for which effective adversarial examples are found, because not always can we find adversarial examples for inputs. And the second one is average distortion rate, which is a distance between original and adversarial input, which shows how much we change the original input to generate the adversarial one. And the average number of queries, which is the number of queries made to the network. Because the making queries to the network is quite costly, efficient approach should make less queries. That's it. Thank you for your attention.